Hey, welcome to yet another episode of YinsPy. Today in this episode, I'm very excited to share with you guys how to apply a sequence-to-sequence model in stock data. So I came across this paper called Neural Machine Translation. It's actually posted online on arXiv, and one of the leading authors is Yoshua Bengio. As one of the top three grandfathers of modern-day artificial intelligence, I love his work. Me personally, I've had a lot of fun reading his work and his paper, and I've learned a lot, specifically when it comes to language processing, NLP, transformer, attention model, sequence to sequence model, BERT, that sort of thing. So I definitely think this is something interesting and will continually to dominate this field for the next 5 to 10 years. So with that being said, let's turn our attention back to the notebook. In this notebook, I start with writing a little bit of a mathematical notation just for my understanding. Essentially, you have a feed-forward architecture. This X bracket 1, it's a very basic building block for recurrent neural network. This is actually a long short-term memory. You have information passing in with your weight, W, and with your bias term. And at each timestamp, you produce something, right? So you have your Y hat, and obviously you can compare that with your Y. Now here, instead of predicting tomorrow's stock price to be, say, $100, which is one numerical value, we're actually predicting a sequence. So in other words, what I'm trying to say here is your Y, it's actually a vector. Now, I don't want to abuse notation here because this is bracket and this is also bracket down here. I'll just verbally say this Y hat bracket something. It's actually indexing the numerical values within the vector of Y. So in this case, Y is multidimensional. Versus these X by itself, it can be a vector or a matrix. So that's going to be how information pass into the architecture. Now you want to go backwards, right? Standard back propagation, we have loss function sitting in the end that essentially compare how far away your educated guess is from the truth. And the first summation is obviously your timestamp, right? Your t. And the second summation here is a k, right? Essentially indexing which value of y that we're looking at. So let's say here, instead of producing a closing price for tomorrow, I'm producing the entire candlestick of information for the stock that I'm interested in. Then maybe this k can be including the highest of the day, the lowest of the day, opening price, closing price, perhaps adjusted closing price, that sort of thing. So all these numbers together form my y vector for that timestamp. And the comparison of that y estimate with the actual real y is going to be the loss function. So with that being said, the rest is just a standard gradient descent. Obviously, when you take loss function, there's chain rule, right? And these things are standard. We find our weights. That's essentially how we train the machine. So with that being said, that's the architecture. Now I want to implement it using Keras TensorFlow. So the first thing I'm going to do is I'm going to start with importing some libraries. So import pandas as PD, import numpy as NP, import yfinance, that means Yahoo Finance, as YF. So now I'm going to initiate some parameters. The first thing is start date. Let's say 2013, January 1st. And then end date, let's make it closer. So 2021, January 1st. And then I have a ticker, say Apple, right? Everyone knows Apple. And then here I have a parameter W, I'm going to call that 1, and then I have my H, and I'm going to call that 5. There are essentially parameters that represent the width and the height of that vector. And you guys will see why I'm calling this way when I'm processing the data. So first of all, I need to download the data. So stock data, that's going to be your YF download ticker start date and date. And let's take a look at the data. So stock data head, that's essentially what it looks like. So we have a date index, January 2nd, 2013, and we have our opening price, highest price, lowest price, closing price, adjusted closing price, and volume. The first thing I'm going to do is kick out volume. So stock data is defined as stock data. I'm kicking out number 5. So 5 means excluding 5, right? So 0 to 4. That's going to give me a new data frame, but the volume is gone, right? So now with the data downloaded, I can define my x and I can define my y. So let me put a little note here. My x is going to be the explanatory data matrix. This is the matrix that my machine is learning from. Okay, so it's going to be some information in the past. I also have my y matrix, which is my response data matrix. This is going to be the matrix that I want to produce, right? I want to predict. So whatever this y is, it's going to be having timestamp later than x. With that being said, I am going to define it. So y is going to be stock data, location, starting from, say, 1. So what does it look like? Y hat looks like that. You see how the data starting from 2013, January 2nd. Now here it's January 3rd, right? The first line is gone. So that's my y. And now I need to define my x. So x is stock data, location 0 to, I'm going to make sure it's integer, stock data dot shape. 0 means number of rows, minus 1. And this essentially gives me my x. We can preview this x and it will give me something like this. Now, as you can see, the first row is actually still January the 2nd, right? So the first row of x is January 2nd, the first row of y is January 3rd. What is happening is I am looking at the things in the past to predict the next day, which is in the future. So I'm looking at January 2nd and I'm predicting January the 3rd. So that's essentially what this data looks like. And now I have my x and y, I'm ready to go, right? To finish up the data processing procedure, I just need to split training and testing. So the first thing I'm going to do is have a cutoff. I'm going to define that as 0.8. So this cutoff is a numerical value between 0 and 1. If it's 0.8, that means I'm taking the first 80% of the data as training set, and that's going to be the observation I'm training my machine on. And the rest 20% of the observation, the machine has not seen it before. So when I check out the performance of the machine, I will be looking at the test set performance, which is relatively honest and fair because the machine hasn't seen it before. So the x train is going to be x location 0 to this index, x shape 0, that means number of rows, times, as you can probably guess, that's cutoff. And then I have my x test. That is going to be location round x shape 0, that's number of rows, times cutoff, all the way to x shape number of rows. So that gives me my x train and my x test. And for y, it's exactly the same code, so I won't bore you with that. I'll just copy paste down on my notebook. So with x train, x test, y train, y test being defined, now I'm going to reshape this x train and x test into an array that with the dimension w and h. So what I'm going to do is x train, I'm going to redefine that with the following. NumPy array x train reshape x train shape 0, that means number of rows, and then w as width, comma, h as height. And I'm doing the same with x test, which is NumPy array x test reshape x test shape 0, w as width, comma, h as height. This will give me x train and x test. Now I'm going to check out the dimensions. So dimensions is 1 to 5, 1 to 5, that's good. This is 1600, this is 1611 versus 403. Kind of makes sense, right? The first 80%, that's my training set. The rest 20%, so 4 by 1, that's 16 by 4. That kind of makes sense. And since now I have my data pretty much ready, so I'm able to move forward and define the actual component and architecture of the modeling part of the architecture. So I'm going to start with importing some libraries from Keras, models, import sequential. From Keras, layers, import depths. Now sequential is actually telling the machine that I'm about to code something line by line. So these layers are added line by line with an order. It doesn't necessarily mean RNN, right? So it's just a naming convention. The next thing is called dense. This actually is not referring to RNN layer. It's just a neural network layer. It does not necessarily have the sequential flavor in it. The next thing I'm going to do is import keras layers. I'm going to call it LSTM. This is the building block of RNN, right? It's short for long short-term memory. And last but not least, keras layers import dropout. Dropout is a functionality in the code to avoid overfitting. If I have a large number of neurons for a particular layer, dropout is essentially saying, hey, I can initiate dropout to be 10%. I can drop 10% of 1,000 neurons at that layer when the training process hit that layer. So that's kind of nice to have, and that's going to be the functionalities I'm importing. So with that being said, now the rest is just to design the architecture. So the naming convention for myself is to call a regressor, and since we're trying to predict numerical values, so it's kind of like a regression problem versus a classification problem which you're trying to predict labels. So regressor, just to make sure that a little bit of a distinction in naming convention, that makes sense. So regressor is going to be sequential. I can design this as regressor add. That's going to be my first layer, so LSTM, that's the building block of RNN. Units, say 50. Return sequence, obviously that's true. And the input shape, as you can probably guess, it's a tuple of something, right? Specifically, we have width and height. So now I have my first layer. I can start adding the next layer. The next layer, I'm going to add a regressor dot add dropout, and let's say 0.2. So this 50, every time I hit this layer, I'm dropping 20% of these 50 neurons randomly. And the next one is regressor. Maybe I'll have another LSTM units to be, say, 50, return sequences to be true, and I'm going to move on to the next layer. I'm going to just copy this because it's essentially doing the same thing. And from here, I can pretty much wrap up the LSTM. And from here, I can pretty much wrap up my LSTM and start adding neural network layers. So regressor.add dense. And the number of units, which is number of neurons, I can give it 128. And then maybe I copy a couple more times, right? And just make it a little bit more complex. And then in the end, I have my last layer to be dense. And here I need to pay attention because I want to plug this in with my Y train. Okay, Y train has its fixed dimension. It can be anything I want. So here, this last dense layer, this unit, has to match the dimension of Y shape. So here, we're going to directly call Y train, and the shape is 1. So we're taking the number of columns. So boom. That's going to be my architecture of this regressor. It's a sequentially designed RNN that is a sequence-to-sequence architecture. We're inputting a sequence, we're outputting another sequence. So we can take a look at the summary, regressor, summary, and it will give me essentially what I've just done in a nice table. Now, that's going to be the feed forward direction, and I'm done. Now I need to train it and essentially produce some sort of results. So what I'm going to do is regressor, compile, and the optimizer, I'll just call it Atom. And I actually have another tutorial walking people through Atom optimizer from scratch. I'll put the link below, just for those who are interested to see. The last function here, I'm going to use mean square error. Okay, so once I compile the model, I can just fit it. So I'm going to say .fit, and I'm going to feed in xtrain, ytrain, epochs, let's say 30, and batch size. That's going to be, say, 64. So batch size means that every time I train a machine, I use 64 observations. instead of the entire dataset in the training sample. So I run it, and it will start training the machine. And as you can see, hopefully the loss is getting smaller and smaller every epoch that I train the machine. And this is still pretty big, right? Because we didn't spend a whole lot of rounds to train it. This is only 30 rounds. So hopefully we get some sort of results. So to visualize the results, I need to make some plots. This function we're gonna use to make the plot is called MPL finance. So I'll just import it as MPF. And then the actual design of the frame, I'm not going to bore you with that. I'll just copy it here. These line of codes essentially means, hey, I want this style, I want this font size, I want this figure size, and that's how many subplots I want. And the first thing I'm going to do is to call MPF plot. And then I want to plug something in here. And then this type is going to be candle because I want candlesticks, right? Style, say Yahoo. This axis is going to be AX because that is the first location of the frame that I'm going to insert this graph in. So this is going to be AX, and then volume is going to be false because we kick it out. And now I'm going to plot something else, right? As you can see, XXXX, type, candle, style, and this Yahoo, and X. Here, where is it going to be defined at? It's going to be defined as AV. Okay, so which is why here I have two lines of subplots to ensure that I'm plotting them together, right? Both plots have to happen together. So as you can probably guess, one of them is real, the other one of them is predicted value. Okay, so before I do this, I need to make some predictions. I'm going to open up a new coding box. I'm going to say predicted stock price is going to be regressor. That's the trained model. Predict X test. And I'll just rename it something else called a real stock price just to match the name for predicted stock price. And that's going to be simply my Y test. So as you can probably guess, predicted is generated by machine. Before that, machine has not seen this data before. Real is the actual stock price. And we're going to make a comparison to see if they're close enough, if they look like each other. But before I move on, I want to make sure that these two data frames match their column names and row names. So if you take a look at predicted stock price, it's kind of like a NumPy array. So there's no rows, there's no columns, not clear, right? So I'm going to process this a little bit. So here I reshape this predicted stock price into essentially number of rows by shape 2. So what do I mean by that? If you print out the predicted stock price shape, it's actually 403 by 1 by 5. And this is because in the beginning, we have the W and H, right? We reshape into a matrix 1 by 5. But now I want to kick out this 1. So I'm going to shape it 0, which is 403, and this 2, which is calling this 5. So this way, I can actually process into a much nicer shape that matches the actual real stock price. So predicted stock price shape is 403 by 5. So this 1 is gone. Now I need to redefine the names of columns and indices. And this is just to make sure that when I plot them together, the dimensions kind of match. Okay, so what I'm going to do is, I won't bore you with that. I'll just copy this. I'm converting back into a data frame, and I'm changing the columns and the index. Column is the column name, index is the row name. So I do that, boom. Now I can just plug it in. The first thing is going to be real stock price, and the second input of the data is going to be predicted stock price. So now I have some sort of plot going on. As you can see, up there, the candlestick up here in the first plot on top, that's a real stock, right? So the one in the bottom, which as you can see right now, it doesn't do much. It's kind of like a white noise, right? It kind of goes like a straight line, maybe some big tails up and down, but then they're kind of like the same height, right? Same height, same distance. It kind of like a white noise. It doesn't really do anything. So we have some predictions, it's just really bad. Okay, so what I'm going to do is I'm going to do some tuning, and we're actually going to come back and come up with a prediction that it matches this real stock data much better. Hey, I'm back. So what just happened was I went off screen and I kind of did a little bit of tuning. And to make my life easier, I actually pack everything into this function, which I call it neural sequence translation. It is a function that is open source published on GitHub, and I'm gonna put the link below. And it essentially soft code all these parameters, right? Number of units, number of hidden layers upfront. So allows me to run this function many times with different number of parameters. So I did a little bit of tuning, and it turned out, I'll just show you the results real fast, that you can essentially, after 120 epoch, you can get your training loss to be as low as 3 or 4. And I would say that if you can do that, then your prediction should be pretty good. So looking at the results, we have two plots, one on the top, one in the bottom. The one on the top is the actual stock data. Okay, so for example, July 9th, we have Apple price to be here, and that is in front of $100. And it goes up and down, goes up and down. Eventually, end of the day, it's about right in front of $140. Versus here, the plot in the bottom, that is the predicted price. That is a predicted stock price. As you can see, in terms of trend and overall up and down, it already matches the real situation pretty well. Say I come back up here and then I go a little bit down and then there's a jump here. It even predicted that. And then go all the way up here and that's maybe the top, comes back down just like the real stock price. And then it'll go back up again, come back down just like the real stock price. And then October 30th, between October 30th and November 30th, between that month of time frame, it goes up just a little bit, come back down. This is what we call it inside month, because the highest of the month and the lowest of the month is within the range of the highest month and lowest month previously. So this inside month here, it turned out this machine is able to predict that no problem at all. And then here after November 30th, it break, go up all the way to all-time high, maybe $140, and it's able to predict that as well. Now, I'm not saying this thing is perfect, right? There are a couple of issues here. The most obvious issue is you can take a look at the candlestick that we're trying to predict here. It's all green. So basically what that means is whatever pattern that this machine end up learning, it doesn't really differentiate within a day, it go up and down, right? Within a day, the closing price happen to be always above the opening price. Now, me personally, I'm going to argue that's not going to be the case, and that's actually a false logic. But I can see somebody agreeing with that because the US stock market indeed went up a lot for the past 5-10 years. And hey, if that's a pattern in the data, then maybe that's what the machine is going to try to guess. Of course, in reality, that's not true at all, right? You look at this chart on top. There's some green, there's some red, right? Some days it go up, some days it go down, right? So that's kind of the idea, which basically means within the sequence that we predicted, it doesn't really differentiate up and down, okay? Overall, the long sequence, overall globally, right, we're looking at the entire trend, it has no problem copying it. No problem at all, okay? So that's the first problem. The second problem is, if you look carefully about the numbers, it doesn't match, right? In reality, we start with the low, maybe $90, right? You start from maybe that is about 95, 96, and go down a little bit, touches 90, and jump back up. And then maybe the high is right in front of $140, come back down to $110, go back up to $140. The candlesticks that the machine predicted indeed went down and then went up. That's true. But here, we actually poke below $90 a little bit. Okay? And then when we come back up, we only hit 105. And it kind of just stopped in front of 105, hobbling around, and then try to come back up again to break that 105. Well, I'm going to argue this is going to be an area of improvement. And we probably need a little bit more tuning. And I think this issues happen between the range of prediction. That takes a little bit more work, right? In reality, it's $90 to $140, but with your prediction, it's only from $90 to 105. And that's a much smaller range than in reality. So, in other words, whatever patterns that the machine is trying to learn, it did not take that range into consideration. Somehow, it hadn't successfully learned that. Maybe just because I haven't feeling more data for it to train. That's totally possible. Or maybe our model is not sophisticated enough. Maybe we need more layers. Maybe we need more neurons. Maybe we need to build an actual neural machine translation with the encode and with the decode. Maybe that will take care of this problem. So hopefully you share my excitement for this project, and definitely you can see this overall trend matches the reality, which actually I'm surprised to see that happen. So there you go. Hope you like this episode. It's a lot of information packing together. Hopefully you're just as excited as I am about neural machine translation, about sequence to sequence model. And if you like the video, give a like and hit the subscribe button, and I'll see you in the next episode.